I joined Bloomberg 6, 7, 8 years ago. It's been a long time. And we have some unique business problems in my group. Primarily, this is a talk about distributed systems architecture, but Python is the vehicle to do that. And there are a lot of specific Python tips and tricks. But a lot of the general ideas will transcend languages and be applicable in Ruby or any other language you're using. So the group that I work in is the Structured Products Group. We are responsible for things like mortgage-backed securities. Recently, for example, cell phone lease deals started becoming securitized. So any bonds based on consumer debt is what we service. It's very interesting and difficult because there are millions of securities. There's a huge number of them, and they're all unique. Cell phone lease deals are different from mortgage-backed securities, are different from credit card deals and auto loan deals. The analytics are very CPU intense. The reason for this is we have to simulate our behavior. The person who buys a mortgage-backed security, the value of that mortgage-backed security is determined by whether or not we pay our bills, right? So if you don't pay your $27 a month for your iPhone, someone gets shorted, right? And that's the systems that we build, is to simulate all those potential possible futures and then give you one number that represents your likely value. So we handle billions of requests a day. We handle the full traffic of the Bloomberg terminal, at least 4 mortgage-backed securities. We've scaled so far into the tens of thousands of cores. So it's, it's a decent sized system. I'm not going to stand up here and say that I do this better than Google, but I know how to do this to a decent sized deployment. We have a lot of challenges that make interface and system design difficult. One is that our data varies wildly. We have some documents that are hundreds of megabytes and some that are just individual kilobytes. We have a huge variance in response time, and you can't predict it. Sometimes a request will take 10 milliseconds. Sometimes it'll take a minute and a half, 2 minutes, or even 10 minutes, depending on the depth of the simulation that the customer wants to perform. This makes it very difficult to size and design interfaces. We have both interactive and batch users. So we have customers who are hitting buttons on the Bloomberg terminal and want to see an answer as soon as possible. And then we have customers who want to run hundreds of thousands of securities overnight and get the batch results at the end. Luckily, we have a pretty big win in the sense that our data is infrequently updated. So a lot of what I'm going to talk about is around controlling, is around caching, and specifically in regards to data. If you were building a system that did, let's say, stocks or equities, where the data updates hundreds of times a second, not a lot of these ideas would work, right? But if you're dealing with something where, an email system, where you get a new email, maybe even a couple of times a minute, you can still adapt to these, the ideas in this talk to that problem. So I was advised to just tell you what I'm going to tell you. So this is kind of the summary, right? So design for cacheability, because if you don't, it's going to be hard to scale easily. If you're going for cacheability, you should aim for this concept of immutable responses or statelessness over the HTTP way of time to live. I'll justify all of these summaries, but just tell you up front so you kind of know where we're headed. Every data set is different. So even if you design something to be cached, it's very important how you cache it. Use message pack and LZ4. Those are fantastic. If you don't know what they are already, you're in for a treat. They're amazing. And turn off garbage collection if you can. That sounds crazy. This is like on the border of being reasonable, but I'll explain why you should do it and how you can do it safely. There's a lot of talk about microservices, and my team and I argued about this before this talk. And so, really, microservices is a buzzword, right? We all know that. The reason I'm pointing it out here is that, to me, the key value in saying microservices is to point out that you're farther on the spectrum to having like small, independently deployable services, right? SOA has been going on for a long time, of course. Microservices is just pushing that to the extreme and deploying more and more units that have more and more interactions. That's important because every one of these arrows is actually a pretty complex interaction. You encode a request. You send the data over the network. You decode a request. You have some actual work, your request processor, and then you do the same encoding and decoding in reverse. Right? And so it seems simple when you look at a diagram like this. But when you actually break down into it, there are dozens and dozens of little small interactions that all can take up time that need to be accounted for. So as I said before, caching is extremely important. And the best way to make something faster is to avoid doing it in the first place. So we're going to talk about how to design cacheable services in the first half of this talk before we get into some of the more Python-specific tricks. So the first thing I want to talk about is TTL caching. Now, I don't actually like this. It just has to be said because it is so common and popular. It allows responses from a service to be reused within a certain time window. It's useful if your services are stateful, if you weren't able to achieve statelessness. But being stale for a short while isn't a big deal. Things like an image on a web page, right? You update it with a better image, but it's okay if some people see an old one for 5 minutes, right? Stuff like that is fine. What's interesting about it is the expiration of the entry is usually determined by the service providing the data, which is great because it means that even though you're aware your data is stale, you can control for how long that data is potentially stale. This is a fundamental part of HTTP. These are the relevant RFCs if you are curious. And the most interesting part of TTL caching for me is that it usually is exposed outside of your system as opposed to other forms of caching. With TTL caching, one of the intended benefits of it is that a middleman like your ISP, AT&T, Time Warner, or your browser, Firefox, Chrome, or Internet Explorer, can read the cache headers on an HTTP request and store it locally. And that's why sometimes Shift F5 does something different than just F5. So this is actually a pretty unique feature. That said, there are some big problems with TTL caching. One is if the source, the canonical source of this data, updates the document, it's possible that certain users will see the old document until that cache expires, right? This is obvious. But it happens to all of us. Sometimes you'll have your cell phone out and it'll be on your PC and you're looking at something and you'll see different information on both your PC and your cell phone, right? You don't really want this behavior. It's fine sometimes, but this isn't really the best. And certainly if you use this in a situation where money is at play or something important, it can be a pretty detrimental pattern. So what we should aim for is statelessness. Now this is interesting because in this room before, the first session, in the evolution of API design, we talked a lot about REST. And statelessness is a very important part of REST. But REST only goes so far. Statelessness with respect to client state is one of the key principles of REST. But there's a lot more state than just client state. I'm going to walk you through a terribly contrived example. I had a control for state at many levels, ended up with true statelessness. I hope everyone's aware, but in case anyone isn't, it's just worth pointing out that stateless services are valuable because they can be trivially cached. By definition of being stateless, they are repeatable, reproducible. They can be trivially tested. If you can feed a service the same request over and over and get the same response, well, there's your unit tests, right? And it can be scaled relatively easily by adding hosts. Because you've controlled for all the state, the general assumption is that there's not a lot of centralized resources that are going to be problematic. And you can also cache trivially, so it makes it easier to scale. So to achieve statelessness, the key is that all input should be provided in the request. Now this is great if you have a pure calculator. If you're just trying to do x plus y equals z, then like there's no reason for me to go up here and tell you anything. It's obvious. But databases, user settings, like real business problems make this difficult. So let's contrive an example where we want to build a system to fetch a user's cryptocurrency portfolio. And so in the interest of like clean interfaces, we come up with the ultimate and clean interface. Get me the user's portfolio given a username. Right? And this operation, this request will do certain operations. It will fetch a user's settings, what currency they want their portfolio referenced in, US dollars or euros. Fetch a user's positions, how many Bitcoins do they own, how much Ethereum, how much Litecoin, etc. Retrieve the prices of those coins from an exchange or from your scrape of the exchange. Calculate the portfolio value in the user's fiat currency of US dollars or whatever, and then format the final output, right? So those are the logical operations. You might end up with a block diagram like this. You have some client, calls your method reaches out to your settings database to get the time zone or the currency, reaches in the position database to figure out how many Bitcoins someone has. And then it reaches the security database to figure out the exchange rate of Bitcoins in that currency, right? Very simple, everyone's happy, you pat yourselves in the back for making such a clean design. For just as an example, here's some pseudocode, it's the same 5 operations, get user settings, get your holdings, get the exchange rates, calculate the value, format the output. So we'll do one by one of the 5 operations we said before. This will be more interesting later. Hope you don't mind that I'm using Python as the language for describing the interfaces. From my perspective, a service call and a function are not very different from each other. You can just talk about the interfaces equivalently. So good job. Your user base skyrockets, right? As crypto's popularity has risen, so has your portfolio site. Everyone's happy, your advertising revenue is going up, but you know, all your databases don't really scale that well at this load. So you're like, what do? You have to do something. So you enable TTL caching on your service. And in the immediate term, traffic drops at least to your backend servers. Your customers are happy, but you start getting phone calls. All right, so you basically turn caching on the get portfolio section. This works for a while. People start calling you. Well, why do they start calling you? Sorry. They start calling you because of that problem I showed you on the TTL slide, where certain users can see different data depending on which cache they're reading from. So in a situation like this, if the user changes their currency or they buy something and you have caching turned on this layer, it might be 5 to 10 minutes before they see their change. Now obviously this is contrived. You would never do TTL caching in an environment like this, but I hope it illustrates why you'd want to avoid it in any real context. But let's start to factor pieces out of this problem. Let's control for user state. So by fetching the user settings before the cache, right, now the user settings will not be subject to the TTL timeout, right? It's pretty easy. Not that complicated. So if you were to look at in pseudocode, you basically now have two functions. You'd have a function that gathers some state, it calls getUserSettings, and then passes into the cached function the currency the user wants. So that this currency, at least, is no longer part of the state fetched by the worker function that is cached. Unfortunately, it doesn't solve all the problems because changes in the position and security database are still likely to cause issues for your users. So you want to control for data as well. So to do that, you need a pattern that allows you to access your data in a stateless way. The way that we use at Bloomberg in our REST environment is immutable documents. When I say Bloomberg, I mean my group at Bloomberg. We're a very big company, of course. Within my group, we use the immutable documents pattern. So we have a very small relational table that is stateful, that has the entity that you're interested in. In our case, it is a financial instrument, a bond, let's say. And then you have the moment in time in which the data updated, and then you have a URL to an immutable document that we guarantee will never change. This database can be junk. It can be anything. It could be a relational database. It can be a key value store. It can be something fancy like Cassandra. It does not matter. What matters is that that document that's in it will literally never change, which now means you can cache the heck out of it, right? You can cache it all day, and it'll never change. Now, this pattern might not always work, right? You might not want to store your whole document over and over and over again. There's a lot of waste here. But you can manipulate this pattern in a few ways to still get the benefits. The whole key to this is that you're leveraging time to freeze your data, right? So you might not have a two database solution with a timestamps table and a immutable object store. You might just have a table with records, right? Let's say these records, each one correlates to an email. If you put a timestamp on every email that you receive, you can ask the database for the most recent timestamp. In this case, it would be 24 for entity B, user B. And then you can say, when you access the data, you pass that timestamp back in. So you can say, give me all of the user's emails at moment 24. And now that can be cached perfectly because you will never add new data at moment 24 again. So if the user is sitting at their desktop hitting F5 over and over and over again, because we all do that, right? F5 over and over and over again. They're going to get 24 every time, over and over and over again. And you're going to hit your cache every time until they get a new message. Then a new row is going to come in with 33, right? Now they'll miss. You'll call the getData function again, enter that right into the cache, and then every other F5 will hit that one. Now, it's not that brilliant, right? But the obvious thing to do is not have this column and then have every single lookup to your data be stateful. So by just thinking about it a little bit in the beginning, you can make huge improvements in the cacheability of your data stores. Again, this doesn't work if these objects update too quickly, so you have to juggle that, of course. These are what those queries would look like, right? Select the max timestamp from table where entity equals B, and then select data from table where entity equals B and timestamp less than or equal to 24, right? That's how the query would look. And you just promise yourself in your contract with your developers that you will never update any rows, right? This is append only. You insert entries, you don't update them or delete. So what are the benefits of this? Well, database reads can be cached as well as any service that depends on it, right? This is very important. Not only can you cache the database, you can cache the entire application stack above it. Batch jobs can freeze the timestamp to ensure consistency. This is a very common pattern at Bloomberg. 4 o'clock when the markets close, everyone wants to run their entire portfolio at the market close and see what the value is, right? But we keep processing data all day, right? Europe is still operating, or Asia is still operating when New York closes. So we can't just like stop writes to the database. So this allows us to use the timestamp to freeze what the application sees and do a nice consistent job for the users. Another thing you can do is you can perform rollbacks very easily. So this happens, right? You mess up the production database. Someone fat fingers something, and you get a whole ton of bad records. So in the past, what do, right? You'd scramble. It'd be a huge emergency. You'd try to find a backup, or you'd try to write a script to delete. That script could cause more damage by deleting the wrong things. So what we do is we just have a global variable somewhere, some global state in the system that says this is the max timestamp that I will accept. Normally, it's infinity. But when we have an emergency, we set it to the exact moment, or a second before, the moment that the bad data entered the database. And now we can clean up that bad data at our leisure. Of course, no new data is coming in during this time, but that's a pretty decent fallback strategy, all things considered. Timed releases are just future dated timestamps, right? Pretty nice feature. And point-in-time access is trivially supported. So try to do this if you can. Try to think of a way to make your database time-aware and append only. So once you do that, the entry point, your top-level service, now calls settings to get the user's currency. it calls the timestamp database to figure out the current moment in time the data is accurate as of. And then when it calls the other method, the internal cached method, now it's immutable. Now it's perfect. And so is access to those databases, which means you can put caches in front of all of those green boxes, which is tremendous. So really what happened here? What happened here is we designed our application in 2 phases. The gathering state phase and the immutable zone, which I just made up. Maybe it's better to call that the stateless area, I don't know. But this immutable zone at the system that this talk is based on at Bloomberg, there's 50 to 60 boxes in that area, right? And there's maybe 3 or 4 boxes in the gathering state area. And each one of them are cached independently. So even if I miss the cache on this guy, I'm still hitting the caches on lower level guys. It is very, very difficult to have a true request come in that misses all the caches. I think we calculated that certainly greater than 98, maybe greater than 99% of the requests that hit this system do not actually have to fetch data from the canonical database. The caches are so effective, the request response caches are so effective that like less than 1 out of 100 requests actually hits it. I think it was like 99.84%, I forget. It's pretty good. And then at the end of the day, this is what the pseudocode would look like, right? You have your state gathering function. When it calls the balances function, it passes in the currency as well as 2 URIs, 2 immutable documents. So this guy now is perfectly cacheable. Okay, so now that we've talked a little bit about how to design stateless services, now that you have something you can cache, how do you do it? This is not all that obvious. You'd think that it would be, right? Oh, just get memcache and hook it up. But there are some concerns. So the first thing you have to ask yourself is, what are you trying to achieve? What kind of locality are you trying to achieve? Most people will say, well, I just want to cache everything. Well, then your cache is your database, right? So, you know, where is the middle ground? To answer that, you have to know what is the size of your working data set, right? The hot data set. You know, we obviously have terabytes, huge amounts of data, more than terabytes. But our working set's only a few hundred gigabytes in the system that we're talking about here. And what resources do you have available? So some companies will have a cache as a service solution, where you have some group that maintains a service-based interface to a Memcache farm or a Redis farm, and you interact with that. Some companies won't. Some smaller companies, you might have a series of VMs, but you don't really have the ability to manage multiple different farms or clusters within your VM space, and you like to have a homogeneous set of request processing nodes. And so there's different ways to leverage these different patterns. So the simple ones are single level. So local caching is pretty obvious. On every node, you run a Memcache instance, and you communicate with it. It's great if you have a small working set. It's great if you only need temporal locality. It is generally the case that if somebody asks for something, they will also ask for it again soon, right? It's just how it is, right? If a user logs in, they're probably going to perform other operations. So you might get a lot of benefit out of a cache that is 0.1% the size of your data set if you are able to leverage those kinds of user behaviors. And obviously it has the lowest latency. I'll explain just how much in a second. And then you have the cache as a service solution, which is great because it can hold a large working set and it's a nice abstraction. It's popular in enterprise. If any of you work for a large business, they probably have a cache as a service solution. It's great, but doesn't really it's not a strict improvement on the local cache solution. Oftentimes you need to do both of these and build multi-level caches, which is great. Gives you both low latency and high storage at the cost of complexity. One of my favorite patterns is the one on the right, which is I don't want to use cache as a service. I have a lot of RAM on machines I already have. So I set up a little cache ring myself, and I have both a local and shared cache. But that's like the most work. I just include it because you know, you can often, if you might look around your network and say, you know, I have the instances I'm buying from Amazon have a certain amount of RAM, and I'm not using all of it. What can I do with it? Well, you can run a shared cache on it, right? So to summarize, you can do distributed caching, local caching, and a combination of both, depending on what you need. Now, that said, here are some timings. So I set up a Memcache instance on 3 nodes. Just in general, all the numbers that I have in this presentation, I have code that will generate them and the data file that was used. I haven't posted it to GitHub yet, but just remember my name. I'll try to get it posted to the PyGotham page or maybe PyVideo when it's posted later if you're curious. The scripts are really basic. There's a requirements.txt to get all the dependencies and whatnot. What is important here is that there is a big difference in time once the cache entries start getting larger. If you have small cache entries, it's not as important. But when you get up in size, the properties of the way TCP operates with the slow start that our colleague told us earlier this morning start to rear their head. So if you have connection to a local Unix socket, you're skipping the entire TCP stack altogether, right? You're not dealing with any packet sizing issues, no TCP, no delay, nothing. And it's very, very, very fast. So if you go with a cache as a service solution, you're going to be in this 10 millisecond area, which is huge, right? 10 milliseconds is a lot. We have a lot of service calls that are less than 10 milliseconds, so caching them could actually be a loss if they return that much data. So it's worth considering the more local cache solutions if you have that available. I mean, to be honest, the multi-level caches are the best if you can manage one. I am pointing this out because I thought it was nifty when I found out. Local Unix domain sockets are so fast that MySQL tricks you into using them even if you did not know that, right? In this example up here, the bottom one is a Unix domain socket, and the top ones are like, so this is like, you know, some IP address colon 112.3. This is localhost colon 112.3, and this is like /temp/file, right? If you try to connect to MySQL on localhost, the client library will see localhost and trick you and go to a Unix domain socket that it knows it's listening on. Why? Because that 4 to 5 milliseconds is huge. This is one of the reasons MySQL can claim to be faster than everyone else. Even though they're really not, they're just the only people that force you to use the faster interconnect even if you're not aware of it. And the last thing I wanted to show you is that the API matters. So I've been using Memcache in production for years, and it's like essential. And we started caching larger and larger and larger objects. When we do Monte Carlo simulations around possible futures, the market environment is what we like vary over time. And the market environments are very big. You have to have the current state of many of financial instruments and over time. So it's a very big item, hundreds of megs. And reading that on Memcache was time consuming. So I said to myself, I asked the question we all should ask, is this the fastest way to do it? And I Googled around, and it turns out there is a binary Memcached API available in Python that just is not very popular. Most of us use Python Memcache. If we just Google for Memcache in Python, that comes up. It's like the first entry everywhere, and it has 99 times the hits the other one does. But this binary guy actually uses Memcache's binary API. Memcache exposes both an ASCII and a binary API. Now, I have no idea if this API actually matters, or if the binary API is just written better. I don't know. What I noticed is that for large documents, it performs about 20% better for free. So if you're using Memcache now and you're happy with it, but you want a little bit more, you might want to check that out. Okay, so IPC is another pretty important part of designing a large scalable system. There are many obscure details that are overlooked. So unfortunately, I don't have the time to talk about all the details. I want to mention TCP port exhaustion because it's one of those like mystical things that you read about every once in a while, and no one's ever really sure if it's happening. It happened to me, and you can fix it. I don't want to tell you now because I have a hard time explaining it properly given the complexity of the topic, but if you make too many connections, client connections, on a given host, you will run out of ephemeral ports, which are temporary ports that are allocated when you open a connection. The way that the Linux kernel recycles those ports is rather slow. It's measured in minutes. So even if you only have 200 connections outstanding at any one time, if those connections cycle quickly, you might end up having 20,000 over a span of a minute, and then you have to wait and pend for one of those to free up. So be aware of this. There are many Linux kernel parameters like TCP timestamps, TCP time wait reuse, SO maxcon that affect this. If you start seeing a latency in your services that you can't find, like you look at your profiling system and your service is responding quickly, but your client's still observing a slowdown, it might be this, and just start Googling. And then also TCP versus Unix sockets is, as I said before, is something that you should think about. If you have like a reverse proxy and the backends that you're communicating with happen to be on the same node, there's really no excuse for not using a Unix domain socket. Like just doing a TCP connection there has no real benefit. If you're going across machines, that's a different story. What I really do want to talk about here is encoding. And the reason I'm bringing this slide back up again is just to illustrate that 6 of the 7 sections in this diagram are related to encoding and decoding responses and then sending the data over the wire. Right? The request processor, I mean, this is not to scale, obviously, but a lot of different interactions occur. Most of us use JSON, and I love JSON. The reason I chose Python, I mentioned this before, is that all of the securities that we cover are unique, right? And we want to have a flexible language to model and represent these in an expressive way. At the same time, I would like my data to be transparent, right? I like to parse JSON. It goes into POD in Python. I don't have to like have an object hierarchy. If I add a new data point, I don't have to go update my object model. Like it's really nice. I update data on my endpoint, my client sees it, everybody in the middle just passes it along unless they need to use it. So I'm going to talk to you about JSON, right? I'm sticking with JSON. That said, I admit and I accept that protobuf, flat buffers, Captain Proto are faster. They just are. But you know, it's kind of weird to use them in a language like Python unless you have a really good reason, because you know, if you want that kind of performance with static schemas and rigid typing, you're probably in C or Go or some other language anyway. So let's talk about JSON a little bit. So there is an ecosystem around JSON. that caters to a lot wider, more use cases than JSON itself does. On this continuum of human readable to fast, you have technologies like YAML and MessagePack on either end. I love YAML. YAML's fantastic. It takes all the things that you don't like about JSON and drops them at the expense of processing time. YAML is great for when you're doing configuration files or anytime you need to present JSON data to users. Right? There's no reason to show JSON to anyone ever, because it's just not easy to see. MessagePack is the opposite. MessagePack is effectively binary JSON. It's what BSON should have been. I don't know why BSON is so terrible, but it is. MessagePack is great. All three of them use the same interface, dump and load, which makes it very easy to adapt an existing application to use one of these. So here's an example, just some trivial data. You can see that on the YAML side, there are no control characters, right? There's no quotes, there's no curly brackets, there's no, yeah. So where in JSON, the quotes are a hint to the JSON parser that this is a string coming up, right? You can trust me it's a string, just go ahead. In YAML, it has to try it. Well, I have an ASCII character. Is it an int? Let me try and parse it as an int. Doesn't work. That's obviously very slow. And then it goes down, trying all the different types in priority order until it gets to the type that actually is there. But it makes things like arrays much cleaner to look at, right? Cooking, comma, home improvement. I'm very domesticated. So you get the idea. So that said, what does the performance of these various technologies look like? So YAML is super, super slow. No surprise. Just don't use it in any context where that matters. JSON's actually pretty good. I mean, look, compared to MessagePack, it's not bad, right? What's important to me about MessagePack is that the load time is much faster proportionally than the encoding time. And in my situation, at least, I encode data much less frequently than I decode it. So that 4x improvement in load time is much wanted. Now, I have a deep copy and cpickle on here, and a column for deep copy, because in the space where I'm working, we copy a lot of data. We might need to, I don't know, you copy data to break cycles sometimes, so you don't have references dangling to things. It's a very common operation. And most of us use the deep copy module just reflexively, right? Why wouldn't we? Python provides a module that does deep copying. Obviously, that's going to be the best, but wrong. That is not the best because it has to support actual Python objects. MessagePack, if you use it to do a deep copy, which is just a dump and then a load, does not support anything other than POD, which is fine anyway for me, because as I told you before, I don't really want to use an object model because that forces me to maintain the object model, right? I love using dictionaries in JSON. So by using MessagePack, all those copy operations got 4 times faster. Even JSON is faster than deep copy because, again, it doesn't support arbitrary Python objects. Even though it's encoding to ASCII instead of to binary like cpickle, it's still more performant. So probably the biggest surprise in the how did I not know that, probably the biggest I didn't know that excessed moments in my last 3 or 4 years was the discovery of this library. We obviously compress everything, right? You need to save data. But we were never happy with the runtime of gzip, zlib, or bz2. I don't know who wrote this. It's amazing. So it is so fast that it is often faster than reading uncompressed data. I know that sounds crazy, right? But the decompression routines are so quick that reading half as much data and then doing a little bit of math in memory is faster than just reading twice as much data. Not all the time. Like if it's cached in RAM, sometimes it's not. But certainly when reading it from a database or reading it from disk. I like to point out this high compression mode. This is like not an obvious thing. They don't really do a good job of exposing this to you. But if you do that, if you pass that high compression mode, the compression ratio will almost reach the efficiency of gzip. And it will actually even decompress faster because now it's so counterintuitive. But because it is smaller in memory, each operation to decompress gets you more bytes. So it makes decompression faster. It makes compression way slower. But it starts to approach the compression ratio of the technologies that we use today by default. And to prove that, I have some statistics. Just as an aside, all of the statistics I'm showing you are based off the same 500 kilobyte JSON file, which I will make available on GitHub sometime after this talk. So you can see that by default, LZ4 is just blazing, right? It's less than a millisecond to compress this 500K document. Decompressing it is almost free. Compare that to zlib, which is 15 times longer to compress and 10 times longer to decompress. If you look at the compression ratios, zlib and bz2 obviously do a better job. Right? So if you encode something once and then decode it 1,000,000 times, maybe you can still get away with bz2. But actually, I wouldn't even do that because the decompression time is high. But you'll notice that LZ4HC's compression ratio is almost there with gzip, almost there with zlib. So you're not giving up much for that incredible decompression time. right, so the last big topic I want to talk about is the garbage collector. So this is probably the most controversial slide. If you're like a purist, you might just want to leave or pretend like I didn't talk about this. So we own a really popular service call that gets called all the time. Even with the caching, even with 99% caching, it still gets called tens of millions of times a day. As I told you before, the magnitude we're talking here is multiple billions of requests a day end up hitting the system. Maybe we're in the tens of billions now. It's a lot. That said, we tried turning off the garbage collector once. I don't know why. I don't know whose idea this was, but it was really effective. We ended up saving about 15% across almost all of our service calls. If you try to make a test for this, it doesn't look as nice. I did some simple JSON parsing, manipulation, and then dumping again, and I saved maybe 5% in the test. This is one of those things that works better with a real job, right? Because real jobs cause the garbage collector to do more interesting things than trivial test cases. So I'll give this a shot. I was embarrassed to talk about this up until a few months ago when I saw a blog post from Instagram about this exact issue. And I said, man, they beat me to it. I should have written about this first. They tried to do the same thing. They had many more problems than we did at Bloomberg. I called gc.disable, done. Everything just worked. At Instagram, they were using some third-party libraries that turned the garbage collector back on, which is really, really dirty for a library to do. You know what's funny is I actually think if you read this post, it was the message pack library, which I also love, so I'm kind of conflicted here. So what they did is they looked into the garbage collector a little more, and they realized there was a parameter called the threshold parameter that would basically disable the garbage collector even if it was technically on, right? So this is pretty nifty. Please read their post. They have a lot more. They go into more details than I do here. But there are some side effects, right? So okay, you turn off the garbage collector, so memory is going to go crazy, right? Sort of. Many service hosts, the WSGI ones for sure, allow you to restart workers periodically. Some of them even let you do it based on the amount of resident memory, which is like perfect, right? I get to 100 megs of RAM, I restart the worker, and then I'm back to 15 again, or however much your worker takes. You can also request a garbage collection manually if you have full control of your framework. Now, not a lot of people can do this. You need to basically return the response to the upstream guy, and then call a garbage collector before you accept a new request. So you're still doing the CPU work of garbage collecting, you're just not doing it while anyone's waiting, right? Now, this gets even crazier. We can talk about reference counting a little bit, or specifically in regards to reference cycles. So, this is a very common pattern in Python. You create something in memory in the local scope, right? So object A is a variable in local scope, which contains object B. Let's say object B is a class called family, right? Object C is a class called family member, and family member has a property on it that points back to family. So if you only have the sister object, you can find the family object, right? So you've now created a cycle between family and family member, right? Not a big deal. We do this all the time. When A goes out of scope, it gets destructed. What's interesting here is the garbage collector didn't show up yet. That's just pure reference counting, right? We forget that you don't really need both. We do have both for reasons like this, but you don't really need both if you can control it. So the reference count goes to 0, it gets destructed, the garbage collector hasn't showed up yet. But this guy, the family and family member, are just kind of out there in limbo. No one points to them, but they point to each other. So the reference counting semantics aren't enough to delete it, and it just stays there. So what happens? Eventually, the garbage collector shows up, and he starts looking around. He's like, I see those two guys. They point to each other, but nobody else. This is like pretty complicated for a computer. They put it all together, figure out that they're an isolated island, and says, you know what, I can destruct both of these. And that's why the garbage collector takes a lot of time, or one of the main reasons that it does. So you can leave the garbage collector on and potentially avoid most of the calculations required with it by breaking these cycles. The way you do that is with something called weak references. This concept exists in any reference counted language. Objective-C has it. I mean, if you search for weak references, you'll see pages from tons of different languages. The idea here is that when C makes a reference to B, it explicitly notifies the reference counter that this is a weak, not strong reference, and not to increase the reference count on object B. So if you look at these, they all have a reference count of 1. Right? So now when A is destructed, well, I don't have a slide for that. When A gets destructed, the reference counter can propagate down through all of them and get rid of them. Now there's some danger to this though, which is that object C, let's say somebody else has a pointer to object C. Some other class, like a dictionary of all sisters in the town, right? that dictionary is going to keep object C alive. So A and B have been destructed. C is still alive, but C is a weak reference to object B, right? This can cause a problem. I had a colleague of mine tell me that this is a very common reason for problems in iOS code because weak references are very popular in Objective-C and things get reference counted and deleted and someone's still holding a reference to it. In Python, I believe that the reference counter will mark that reference or set that reference equal to none so that your code might still fail because it's not expecting none to be there, but at least it won't call a method on an object that has been destructed. So a caveat to this is that even if you try to control for cycles, third-party libraries may introduce unexpected ones. So you really shouldn't get involved in this unless you're awesome. You really need performance, and you have the proper tooling, right? So get a tool like Object Graph that will visualize for you the object dependencies in your system, and then you can get some big speed ups. I mean, we found in our systems that we have a very small number of objects that are referenced everywhere, and those are the ones that were causing the garbage collector to work overtime. Because even if it doesn't find a cycle to break, it still has to iterate through all the entries and do all this work. So that's kind of it. It's kind of the summary section now. So this is a greatly simplified but ultimately true representation of the system at Bloomberg that I just spoke to you about. We have clients. This is a REST system, so those are HTTP clients. We have load balancers that distribute requests across many machines. We have stateful state gathering services like I showed you before that fetch data from the timestamp database, fetch user settings, and then contact a very large network of services in our stateless area, right? They're all behind caching proxies. We use cache as a service for the caching proxies. We then, when we fetch data from our canonical database, that immutable object store that I told you about, that is also cached. That is cached in a multi-level way. The request response cache is not multi-level because you're not really going to see, we have, there's hundreds of nodes in this system, right? So it's very unlikely that any top-level node is going to see the same request in any reasonable amount of time. So that local cache isn't very valuable on the service level for us. But on the database access level, it's very valuable. So we have a multi-tier cache there, and we don't use cache as a service for that. We just use extra RAM, and we have a hash string that we built based on Amazon Dynamo, which is a topic for another time. Amazon Dynamo is great, in case anyone's curious. We stole some of the ideas that we liked. Yeah, that's that. So the summary that I showed you before, just to reiterate it, I know I didn't prove that here, but if you're designing a system today, you really should have some strategy for how you're going to cache things. Because if you don't, scaling becomes infinitely more difficult when you need to scale. Go for statelessness. Do it, right? And go beyond REST. REST, if you read the REST pages on Wikipedia or wherever, REST will tell you, be stateless with respect to client state. Go further than that. Go stateless with respect to your data too. Every data set's different, so don't just blindly use whatever the easiest cache is. Think about it. Do I need a fast cache? Do I need a slow cache? Does it have to be big or small? Am I going for temporal locality? Use message pack and LZ4 if you can. Oh, one of the things I didn't point out here that I wanted to is that these arrows actually represent different forms of data interchange. So obviously to our clients, we're sending back pure JSON. But in between our services, we'll use LZ4 message pack, just because it's that much faster. Right? And it's okay to have a heterogeneous system like this at layers that your customers can't see. Questions?
You have a lineage always maintained, right, from the top to the bottom with the caches?
So I have a lineage maintained. What do you mean by lineage?
So if something crashes down the path, or something doesn't get from point 1 to point 10,
Yeah.
you're able to kind of go in the reverse and pick it up in cache from stage 3 and then rerun.
Yes. So the question is, what happens if there's an error in a deep request, right? So you might have 7 levels of requests, and somewhere in the middle it fails. So how do we deal with that, and are we able to benefit from layers that are cached? The answer is yes. We are aware of errors, and they are not cached. So we have if we have a 500 or an explicit error, not necessarily a 500, but an error code, we will not cache that entry, but the underlying requests that did succeed are still cached. So the second time it comes through, if the error is transient, it will succeed properly and it will be faster than if it was run fresh.
Have you considered, I assume your load balancer is doing something like round robin load balancing across
Lowest pending. The question was, how does the load balancer work? It's lowest pending.
Okay. Have you considered using some sort of kind of sharding load balancer and sending it to specific workers?
Yeah, so this is a great question. We did this. So sharding is a super important part of distributed system design. I didn't talk about it here because it's not fundamental to how we scale, but for a lot of people it is. A lot of people talk about sharding on the database level. So as the question was brought up, it was more about sharding requests. So we used to do this. We used to shard based on the financial security that was being requested in order to make the caches more effective. So if you asked for bond A, we'd go to machine A. If you asked for bond B, we'd go to machine B. And it was great in the beginning, but we had the same problem with that you have when you shard a database. And that is that that strategy has to be really even. What we found is that a very small percentage of securities get a disproportionate amount of traffic. So we would shard on security, and most time it was fine. But these very popular securities would all go to the same machine or the same set of resources and overwhelm them. So we ended up removing that feature. But I think this is a great strategy if you are able to do that. I think the load balancer having some knowledge of your request and being able to shard and pick a backend server intentionally can give you great advantages in terms of cache efficiency. I'm good. All right, thank you very much. We're out of time. I'll be around.